Okay, the next application of the derivatives that we want to talk about is concavity. So concavity and points of inflection are information about a function that is told to us by the second derivative. So when we work these problems, we're going to have to find the second derivative and use that to get the information about concavity. So let's start with these two important definitions of concavity. It says let f be differentiable on an open interval. The graph is concave up whenever f prime is increasing and concave down whenever f prime is decreasing. So that is the definition of concavity. Okay, and then secondly, what I want you to see is that if a graph is concave up, what that means is that the tangent lines are all below the function. Okay, so I'll show you the picture here in just a second to kind of illustrate that. Secondly, if the graph of f is concave down, then the tangent lines are above the function. Okay, so if you look at this picture, that's kind of what this picture is saying. This first graph here is concave up, and you can see that f prime is increasing because if you were to look at this slope right here is a negative slope, and then the slopes become positive. So this is a positive slope. This slope is also positive, and it is a greater slope than this second slope right here. This third one is bigger, and so f prime is increasing. And you can also notice that the graph lies above its tangent lines, or really another way to say that is that the tangent lines are below the function. Okay, similarly here for concave down, so this is a concave down graph. You can see that f prime is decreasing because we started off with a positive slope here, and then we're getting negative slopes here and here, and the slopes are getting more negative as you go along the function. Okay, and also notice that those tangent lines are above the graph, and so that's what makes the graph concave down. Okay, so the test for concavity, we're going to use the second derivative, and we're going to determine where it's positive or negative. So if f double prime is greater than 0, which also means positive, that means that the graph of f is concave up. If f double prime is less than 0, or also negative, is what that means, then the graph of f is concave down. And a point of inflection is whenever a graph changes concavity, either from concave up to concave down, so concave up to concave down, or concave down to concave up. Okay, so that's one of the cases where a function has a point of inflection. The second is when f prime changes from increasing to decreasing or decreasing to increasing, and that just follows from the definition back up here that a graph is concave up when f prime is increasing and concave down when f prime is decreasing. And then the third is f double prime changes from positive to negative or negative to positive. Okay, so what we're going to do now at the bottom of page 4 is kind of summarize all of these theorems and definitions that we've talked about. So in this first column, I'm going to write down f along with its first two derivatives, f prime and f double prime. Okay, well, we learned on page 2 that if f is increasing, f prime is positive, and if f is decreasing, f prime is negative. Now that same information will translate down a level whenever we talk about f prime. What that means is that if f prime is increasing, it means that f double prime is positive, and if f prime is decreasing, then f double prime is negative. Okay, and then by definition, back up at the top of page 4, if f prime is increasing, that means that f is concave up, and so I'm going to draw a graph that looks concave up, and if f prime is decreasing, then f is concave down. This is a chart that you need to be able to recreate on your own. Okay, a lot of the times, if you can redraw this chart on a question, you're going to be able to answer the question pretty easily. And so I would just go ahead and encourage you to have this chart memorized, and so that way you can reproduce it on any question. Okay. So in order to check intervals of concavity and points of inflection, it is always easiest just to look at the second derivative if you don't have a calculator or if you're not looking at a graph. So example 4, find the intervals of concavity and the points of inflection. Okay, so example A, we have this function. We're going to take the first derivative, which is going to say 3x to the 4th minus 12x cubed. And so that means that the second derivative is equal to 12x cubed minus 36x squared. And remember, I'm taking the second derivative because the question is asking me about concavity. Okay, so this is going to equal to 0. I'm going to go ahead and factor out what can be factored out. And in this case, that's a 12x squared. And that's going to leave me with an x minus 3 equals to 0. Okay, so if I set both of those factors equal to 0, I'm going to get x equals to 0 and x equals to 3. And these are what are called my possible points of inflection. And the reason they are possible points of inflection is because I have to actually test whether or not they are points of inflection by seeing if there is a sign change in the second derivative. Okay, so we're going to put 0 here and 3 here. And so if I plug in -1 to the factored version of the derivative, which is right here, that's what I'm going to plug into, is the factored version. Then 12 times -1 squared is positive, and then -1 minus 3 is negative. So a positive times a negative is a negative, and so I'm going to draw concave down in that section, since if the second derivative is negative, that means that the function is concave down. Okay, in the middle section, I could plug in either 1 or 2. Either 1 would be fine. If I plug in 1 for x, then 12 times 1 squared is positive, and 1 minus 3 is negative. And so again, between 0 and 3, the function is going to be concave down. And so what you should notice right now is that x equals to 0 was a possible point of inflection, but it is not an actual point of inflection, since the second derivative did not change signs, which means that the original function did not change concavity. Okay, and then in the last section, we could plug in 4 for x into the second derivative. 12 times 4 squared is positive, and 4 minus 3 is also positive, and so the function is going to be concave up there. Okay, so I'm going to use that chart to now write my answer. This function is concave up on the interval from 3 to infinity. It is concave down from -infinity all the way to 3. And we did skip 0 here and just included it in our interval for concave down. If that confuses you or you don't feel okay about that, then please feel free to contact me and I'll explain that in more detail. But just take my word for it, we are going to include 0 in that interval. Okay, and then there is a point of inflection going on at x equals to 3, since there was a change in the sign of the second derivative. Okay, example B is a similar problem, although it has trig in it, so we're going to have to remember our trig values and some things about the unit circle. So if I first of all take the first derivative, f prime of x is equal to cosine x, and then the derivative of cosine x is going to be negative sine x. And then the second derivative, f double prime, is going to equal to the derivative of cosine is negative sine x minus the derivative of sine, which is cosine. Okay, so if I set this equal to 0 to find my possible points of inflection, I'm going to get negative sine x is equal to cosine x. This is a problem that you should have solved in the first assignment over the unit circle. And so if you'll recall, you should have gotten x is equal to 3 pi over 4 and also 7 pi over 4. Okay, so if we put those on a number line, we can test concavity in these intervals. So 7 pi over 4 will go there, 3 pi over 4 on the left. Okay, well, I'm going to try to keep this to being things that are on an axis because I know the values of those are either 0, 1, or -1, and so it's going to be easy for me to compare whenever plugging into the second derivative. And remember, into the second derivative is going to be into this function right here. Okay, so from 0 to 3 pi over 4, pi over 2 is in that interval, so I'm going to plug in pi over 2 to the second derivative. So I'm going to end up having negative sine of pi over 2 minus the cosine of pi over 2. Well, sine of pi over 2 is positive 1, so this is going to be -1 minus the cosine of pi over 2, which is 0, And so negative 1 minus 0 is negative 1, which means that in this interval, the function is concave down. Okay, in between 3 pi over 4 and 7 pi over 4, I know is 4 pi over 4, or better known as pi, and so I'm going to plug in pi for that interval. So negative sine of pi minus the cosine of pi. Well, sine of pi is 0, minus the cosine of pi, which is negative 1, and 0 minus negative 1 is equal to positive 1. And so in this interval, the function is going to be concave up. And then in the final interval, I'm not going to be able to do anything that's on an axis, but I could, plug in perhaps 11 pi over 6 if I wanted to. So if I plug in 11 pi over 6 into the second derivative, that's going to be negative sine of 11 pi over 6 minus the cosine of 11 pi over 6. Now again, I don't really care about the value necessarily, I just care about the sign. So let's see if we can figure out what this is. This is going to be negative of sine of 11 pi over 6, which is negative 1/2, minus the cosine of 11 pi over 6, which is positive square root of 3 over 2. So what I end up getting here is positive 1/2 minus the square root of 3 over 2. Well, since square root of 3 over 2 is bigger than 1/2, I'm subtracting a bigger number, which means that this is going to be negative. And so in this interval, we are going to be concave down. Okay, so we are now ready to write our answer. This function was concave up on the interval from 3 pi over 4 to 7 pi over 4. The function was concave down on the intervals from 0 to 3 pi over 4, and also from 7 pi over 4 to 2 pi. And the reason I'm using 0 and 2 pi there is if you go back up and look at the problem, the interval that we cared about here was from 0 to 2 pi, and so I'm not going to put negative infinity or positive infinity. And then there were points, whoops, let me go back to the pen here, not the highlighter. There are points of inflection wherever the second derivative changed signs, which would have been at x equals to 3 pi over 4 and also 7 pi over 4.